Hey everyone, welcome back to our series on statistics. This is episode number 5 and we'll be tackling the most beloved distribution in statistics, the normal distribution. The normal distribution is so beloved because it's the most common or normal distribution we observe in real life. Now, what does a normal distribution look like then? It's just one type of distribution where most of the data is clumped around the mean, and as we venture away from the mean, the distribution tapers off. Now, remember in the last episode, we discovered that a parameter is the characteristic that defines the distribution entirely by itself. So take note, a normal distribution has two and only two parameters, the mean and the variance. So given the mean and variance, there is one unique normal distribution that is possible. This is similar to how with two distinct points, we can find one unique line, or with three distinct points, we can find one unique parabola. In other words, if we know it's a normal distribution, then we'll know for sure it will just be defined by the mean and the variance. So normal distributions with different means shift the distributions left and right, whilst different variance shows how spread out the distribution is around the mean. So in this episode, we'll be adventuring through three major topics. Number 1, the empirical formula. Number 2, the notation and properties of the normal distribution. And finally, the standard normal distribution and z-scores. Now, we have a rough idea of what a normal distribution looks like, but how can we quantify its properties? In 1718, Abraham de Moivre published a book called The Doctrine of Chances, which was one of the first textbooks that dealt with probability. By conducting many experiments, de Moivre derived an empirical approximation to the normal distribution, where 68% of the scores lie within one standard deviation, and 95% of the scores lie within 2 standard deviations, 99.7% of the scores lie within 3 standard deviations of the mean. But now I want an actual function to express my normal distribution rather than a few empirical values. So let's go through the notation first. We're going to continue with our random variable as capital X. So the notation then becomes this, because X follows a normal distribution with the two parameters mean and variance. The normal distribution has a PDF of... Yep, I know what you're thinking, but don't tune out yet. As you can observe, it's just solely dependent on the two parameters mu and sigma. The basic structure you need to recognize is this, which is the shape of a normal distribution, what we commonly call as a bell curve. Because if you look hard enough, it looks like a bell. Now, by graphical transformation, we just need to translate and dilute by factors that ensure we satisfy the two conditions of being a valid PDF. Number 1, each probability or the PDF is greater than or equal to 0. And number 2, the sum of all probabilities of the PDF is equal to 1. Now, there are two important properties of the normal distribution we must know. Firstly, the mean, mode, and median are all equal to each other. Recall in episode 4 on summary statistics, we found a statistical approach to calculate the mean, mode, and median. But what it represents visually is as follows. The mean is the point where the entire distribution can balance on. The median is the point where 50% of the area of the PDF lies. The mode is the point where the PDF is the highest. So in a normal distribution, all these 3 points are the same point. The second and last property is that the normal distribution is symmetrical, so we can calculate ranges of probability efficiently. Since the normal distribution is symmetrical, we can deduce that the probability below the mean minus A is equal to the probability above the mean plus A. And because the total area under the PDF is equal to 1, the area above and below the same score will add up to 1. Hence, we can obtain this CDF relationship of a normal distribution because of its symmetrical nature. The standard normal distribution is just one special type of normal distribution, which has mean 0 and variance 1. So you just sub mean 0, variance 1 into the normal PDF and you get this. By convention, we just let the random variable of a standard normal be capital Z rather than X. This is why we refer to the outcomes of a standard normal distribution as z-scores. And we also label the standard normal PDF as function capital Phi of Z. So what's the big deal and why do we even need to use it? We realize that comparing scores of different normal distributions is hard. For example, say Al has $100 Australian where the mean is 88 and standard deviation 10. But Bert, on the other hand, has $120 New Zealand, where the mean is 96 and standard deviation 12. So who has more money relative to their own country? To answer this question, we need to transform the X scores within each normal distribution into Z scores of the standard normal distribution. This process is called standardizing the score, and it allows us to compare the scores across different normal distributions. So how do we standardize our scores? We first need to understand what linear transformation does. Say we have a normally distributed random variable x. Then we just create another random variable y as a linear transformation of x. If you multiply a constant to x, you multiply the mean by a as well, but you multiply the variance by a squared, as variance is a squared measure, so it has a squared effect. If you add a constant to x, you shift the mean by b, but shifting has no effect on the variance. So as you can see, y just follows another normal distribution but with different parameters. If that didn't make sense, make sure you get this bit. We want to create a standard normal distribution with mean 0 and variance 1. So starting from a normally distributed x, strip off the mean, and then divide by the standard deviation. Remember the squared effects. We just created a new normal distribution with mean 0 and variance 1, which is the standard normal. So by stripping the mean and dividing by the standard deviation, we obtain the z-score. So why is standardizing helpful? A practical reason is that the normal distribution PDF is a bit too much, but we have a nice and easy table for the standard normal distribution, which is called the z-table, and it records the CDF of the standard normal. The vertical axis shows the unit place of the z-score, whilst the horizontal axis shows the first decimal place. So, what is the probability that someone in Australia has less than L? Again, we just strip off the mean and divide by the standard deviation from the score. This will standardize the score into a z-score. Finally, we extract the probability from the z-table. So we can conclude that Al's income is in the 88th percentile in Australia. As you can probably notice, the z-table only contains CDF values, but we can still use it in a variety of different ways. Number 1, we can calculate the probability above a score by first finding the CDF and then subtracting it from 1, the total probability. Number 2, we can also calculate a probability range by subtracting the individual CDFs from the table. And finally, number 3, we can go backwards and find the z-score required for a certain probability from the z-table. So that's it for episode number 5. We tackled everything about the normal distribution from its empirical formula to all of its properties. We also learned how to avoid the yucky formulas of the normal distribution by standardizing to z-scores and using z-tables. So tune in for the next episode to mess around with a different beast, the binomial distribution, or click here to watch the episode 0 on the big picture of statistics. So like, subscribe, leave a comment below on what you'll like to learn in the future. I'll be there.